Hello, my dear students. Let us take the second case, that is strain energy stored in a body when the load is suddenly applied. Okay, in the last class, I discussed about strain energy stored in a body when the load is gradually applied. Today's class, we will discuss on when the load is suddenly applied. So, sometimes what happens in the factories and workshops, the load is suddenly applied on a body. For example, when we lower a body with the help of a crane, the body is first of all just above the platform on which it is to be placed. Okay, if this is the just scenario, like when you want to lower a body with the help of the crane, the body is first of all just above the platform on which it is to be placed first. If the chain breaks at once, at this moment, the whole load of the body begins to act on the platform. Suppose there is a failure in the chain, so it breaks. What happens? You just imagine the whole load of the body begins to act on the platform. Now this is a good example for sudden load. Okay, so means you just imagine when you want to lower the body on the platform. Okay, but what happens that hook or the chain, no, it breaks it breaks suddenly. So what happens, the entire load of the body that begins to act on the platform at a time, so that is called as sudden load. For example, now let us consider a bar subjected to sudden load. What are the terms you have to consider here? P is equal to load applied suddenly, and A is equal to cross sectional area of the bar, and L is the length of the bar, and E is modulus of elasticity of the material, and delta is the deformation of the bar, and sigma is stress induced by the application of sudden load. Okay, so we'll see what is the formula for the strain energy stored and the stress in this case. Since the load is applied suddenly, therefore the load is constant throughout the process of deformation of the bar. In this case, what happens? The load is applied suddenly, so the load is constant throughout the process of the deformation of the bar. But in the previous case, what was that? When the load is gradually applied, means the average load we have taken, because it was 0 first, then it increases to P. So the average load was taken. But here the load is constant throughout the process of the bar. So the P is equal to P only. So what is work done? Work done is equal to force into distance. So force is now load, that is P, and deformation. Delta L is deformation. So simplify this, you get, we know that strain energy, the last derivation I have told how you get this U. U is equal to, strain energy is equal to sigma square divided by 2E into A into L, or volume. Okay, same method, only the difference here, in that case it was P divided by 2, but here it is P. Okay, so since the strain energy stored is equal to the work done, so what happens now? The sigma square to sigma square divided by 2E into AL, that is equal to now P into delta L. So P into delta L is nothing but sigma divided by E into L. Why this is? The formula we know. In the first chapter you studied, delta L is equal to PL divided by A into E. So P divided by A is sigma, stress is equal to load divided by area. So delta L is equal to sigma into L divided by E. Substitute that, you get here sigma is equal to 2 into P divided by A. Okay, in this case, stress can be calculated by using this formula, 2 into PA. In the previous case, we have just considered sigma is equal to P divided by A, but here this formula for the stress is 2 into P divided by A. It means that the stress induced in this area is twice the stress induced when the same load is applied gradually. Once the stress is obtained, the corresponding instantaneous deformation delta L and the strain energy may be found out as usual. Okay, the strain energy formula is same, only the stress calculation is here different. Means you have to consider twice that of the load divided by area. So let us see some examples how to calculate the strain energy when the load is applied suddenly. Okay, let us take this example. An axial pull of 20 kilonewton is suddenly applied on a steel rod 2.5 meter long and 1000 mm square in cross section. Calculate the strain energy which can be absorbed in the rod. Take E is equal to 200 GPa. Okay, this is given. Here it is mentioned suddenly applied. So you have to use that formula. So what is given? Pull is given P, that is 20 kilonewton, 20 into 10 raised to 3 Newton, and length of the steel rod is 2.5 meters. So 2.5 into 10 raised to 3 millimeter. Then cross sectional area is 1000 mm square. Modulus of elasticity is 200 GPa or 200 into 10 raised to 3 Newton per millimeter square. So first let us calculate. We have to find the strain energy. So strain energy formula is U is equal to sigma square divided by 2E into V. So we don't know what is the sigma. So let us calculate first that. How we can calculate? We know that stress in the rod when the load is suddenly applied, sigma is equal to 2 times of P divided by A. Okay. So 2 into load is given 20 into 10 raised to 3 Newton divided by area. Area is 1000. So simplify this, you get 40 Newton per millimeter square. Okay, area you know, stress you calculated. Now you have to calculate what is the volume of the rod, because this V is there. Volume is nothing but area into length. Area is 2.5. Sorry, area is 1000, 10 raised to 3 into L. L is 2.5 into 10 raised to 3. So simplify this, you get 2.5 into 10 raised to 6 mm cube. Once if you know sigma and V, you can calculate what is the strain energy absorbed in the rod. That is U is equal to sigma square divided by 2E into V. So sigma square, that is 40 square divided by 2 into E is equal to 200 into 10 raised to 3 into volume is calculated value 2.5 into 10 raised to 6. So when you simplify this, you get U is equal to 10 into 10 raised to 3 Newton millimeter or 10 kilonewton millimeter. So like this you can calculate what is the strain energy absorbed in the rod when the load is applied suddenly. Okay, let us take one more example on this. A steel rod of 28 mm diameter is 2.5 meter long. Find the maximum instantaneous stress and work done at maximum elongation when an axial load of 50 kilonewton is suddenly applied to it. Also calculate the maximum dynamic force in the rod. Take E is equal to 200 GPa. Okay, this is given here. The diameter is given, that is 28 mm, and length of the rod is 2.5 meter or 2.5 into 10 raised to 3 millimeter, and axial load that is given 50 kilonewton or 50 into 10 raised to 3 Newton, and elasticity, modulus of elasticity is 200 into 10 raised to 3 Newton per millimeter square. So first we have to calculate what is the stress. Here it is asked to calculate maximum instantaneous stress. Okay, so how you can calculate stress? This is the load is suddenly applied, so stress is equal to 2 into P divided by A. So for that we required area is not given here, so we have to calculate area. How you can calculate area? This is a rod, so diameter is given, so you can calculate area. So cross sectional area of the rod A is equal to pi divided by 4 into D square. So pi divided by 4 into D is 28 square, so you get 615.8 mm square. So this is area. So now you can calculate what is the maximum stress, instantaneous stress when the load is suddenly applied. That is equal to 2 into P divided by A. So 2 into P is given 15 to 10 raised to 3 divided by A 615.8. So you get 162.4 Newton per millimeter square or 162.4 MPa. So now we have calculated maximum instantaneous stress. Let us calculate what is work done and what is the maximum dynamic force. So work done, that is given by the formula P into delta L, that is work done, means the load into the deformation or force into the distance. So here for this we require delta L or elongation or the deformation. How you can calculate? The deformation is equal to PL divided by AE. So P divided by A is equal to sigma stress. So stress into L divided by E, that is delta L. So calculate sigma, substitute what is sigma max, that is here it is calculated value 162.4 MPa. So substitute that into L. L is 2.5 into 10 raised to 3. It is given 2.5 into 10 raised to 3 divided by E. E is Young's modulus 200 GPa or 200 into 10 raised to 3 Newton per millimeter square. So you get deformation is equal to 2.03 mm. Once if you get the deformation, you can calculate what is work done. Work done is equal to load into the deformation. The load is given 50 into 10 raised to 3 into the deformation is 2.03. So you get work done is equal to 101.5 into 10 raised to 3 Newton millimeter or 101.5 kilonewton millimeter. So this is work done. After that, it is also asked to calculate what is the maximum dynamic force. So maximum dynamic force it is asked. So force is equal to area into stress, that is the force. So the dynamic force is equal to area into stress maximum. So area is calculated here 615.8 into sigma maximum is 162.4. So you get 100 into 10 raised to 3 Newton or 100 kilonewton. Okay, so like this you can calculate the stress, you can calculate what is the instantaneous stress, what is the work done, what is the dynamic force, what is the strain energy stored when the load is applied suddenly. I hope all of you understood. Thank you.